Hey there, Calc 2 crew, and welcome back to the Daily Problem Sets. Today we're going to take a look at power series. Very excited to talk about power series today. We'll just go over a little bit of this quickly. Remember, you should have already watched the lecture video for this section. We're just going to take a look at some more examples now. Power series is a series of the form, we have the sum from n equals 0 to infinity of c sub n times x to the n. And if we write this out longhand, we just get this infinite degree polynomial, c sub 0 plus c sub 1 times x plus c sub 2 times x squared plus c sub 3 times x cubed plus so on and so forth, very generic, where x is a variable and all the c sub n's are the coefficients of the series. Similarly, we could have a power series in x minus a, and this would be referred to as a power series centered at a or a power series about a. It's very similar. Here we have the sum from n equals 0 to infinity of c sub n times parentheses x minus a, all to the power of n. And this is just going to be centered a bit differently, so now centered at some value a. We could actually say that the definition above is centered at a equals 0, but for some non-zero a, we would have c sub 0 plus c sub 1 times x minus a, c sub 2 times x minus a squared, c sub 3 times x minus a cubed. We're adding all of those. And again, where x is a variable and the c sub n's are the coefficients. And we have a really nice theorem here. So if we're given a power series, the sum from n equals 0 to infinity of c sub n times x minus a to the power of n, there are three possibilities. We could have that the series converges only when x is equal to a, which is, very underwhelming, not very exciting. We could have that the series converges for all x, or we could have that there is some positive number, capital R, where the series converges if the absolute value of x minus a is less than r, diverges if the absolute value of x minus a is greater than r. And what we're going to do in this section is we're going to take a look at, we're given a power series, and we want to determine whether or not we have that power series is going to converge on some radius. We want to find that radius of convergence. We also want to find an interval of convergence as well. So we're going to start by using ratio test most likely. So we say in general, the ratio test, sometimes the root test, should be used to determine the radius of convergence, capital R. Remember that the ratio and root tests always fail at the endpoints of an interval of convergence. So we have to check those endpoints manually with some other test. And if we want to sort of remember what the ratio test looked like, let's talk about the ratio test here. We're looking at the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. And this gives us some value L. We have, if L is less than 1, we have absolute convergence. If L is greater than 1, or if L is not finite, we have divergence. And if L is equal to 1, it's inconclusive. And this is what we mean when we say that those endpoints is where ratio test is going to fail. We have to check those manually with some other test. But let's go ahead and take a look at a first example. I want to find the radius of convergence for the series. Here we have the sum from n equals 1 to infinity of x to the n divided by 9n minus 1. And what I'm going to do first is I'm going to say, okay, so what I'm looking at, my generating term is a sub n, which is x to the n over 9n minus 1. And if I want to find a sub n plus 1, that means just replacing any mention of n with n plus 1. So x to the n plus 1 over 9 times parentheses n plus 1 minus 1. And I could expand this out to clean it up a bit preemptively. We have x to the n plus 1 divided by, it's going to give me 9n plus 9 minus 1, so that's plus 8. And this is what I want to work with. And remember, I want the limit as n goes to infinity of the absolute value of, I want a sub n plus 1 on top, so that's x to the n plus 1 divided by 9n plus 8. And then all of this gets divided by a sub n. A sub n is this x to the n divided by 9n minus 1. And I don't want to divide a fraction by a fraction. We want to instead multiply by the reciprocal, so we'll say limit as n goes to infinity of the absolute value of, I leave the numerator the same, x to the n plus 1 over 9n plus 8. And then I multiply by, I flip this, the bottom fraction, so 9n minus 1 over x to the n. And we'd like to clean this up. So let's see what we can do with this from here. So we have the limit as n goes to infinity, absolute value of, now I can break up x to the n plus 1 as x times x to the n divided by 9n plus 8, and then times, I'll leave this alone, the 9n minus 1 over x to the n. But I see that the x to the n on top and bottom is going to cancel. So I get the limit as n goes to infinity, the absolute value of, and here I'm going to put the n terms to the beginning, so that's 9n minus 1 over 9n plus 8, and then times x. Sort of write that separately, but still inside the, looks like I'm dragging something with the stylus, but I got it. I'm on it. Still inside the absolute value. Bam, looks good. So now from here, what I want to do is I want to try to work with this expression on n, since that's what the limit is affecting. Let's use our favorite algebraic trick. Divide by the highest power of n in the denominator. So that's going to be 9n over n minus 1 over n divided by 9n over n plus 8 over n, then times x. And I can reduce. So say limit as n goes to infinity, absolute value of, and now I have 9 minus 1 over n divided by 9 plus 8 over n, and then times x. And as n goes to infinity, 1 over n and 8 over n both go to 0, so I can actually take the limit now. Get absolute value of 9 minus 0 over 9 plus 0, and then times x. We say, well, this is 9 over 9, which is 1, so I just get absolute value of x. Now this is where we have to have a conversation, because I just did ratio test. We're used to, in the previous section, doing ratio test and getting an answer out. We're getting some numerical value, getting something that's either infinity or some finite number, right? And from that, we make a judgment. We say what the result should be. This isn't going to happen in this section. It's not going to happen with the power series. What I get out is still my limiting value, capital L, from ratio test. So I say this is capital L. And I have to now work with this hands-on. So I have to make this connection to the result of ratio test. Ratio test isn't going to make it for me in this case with the power series, but I have to remember what ratio test says, because this is going to be conditional. It's not really going to say, okay, so this does or doesn't converge. It tries to give me an idea as to when it will converge, but I have to be willing to bring it to the next step. So remember, when L is less than 1, we have this absolute convergence. What I got for L is not a numerical value for me to judge, but it's an expression for me to work with. That's the big distinction here. This is something that I now need to do my due diligence with. So we'll say, okay, this is what I have for L, and I can tell you when it's going to converge. So we'll say when the absolute value of x, which is L, is less than 1, we have this absolute convergence. And so this is telling me my radius of convergence. This says my radius of convergence is capital R equals 1. And right now, I'm actually getting some rough idea for an interval of convergence. We'll call the interval of convergence capital I. And this is now telling me, so long as the absolute value of x is less than 1, meaning x is between -1 and +1, we have convergence. I can guarantee you that at this stage. But the question is, what about the endpoints? Because the problem is, I'll do this in a different color, red, because red means we have a problem. The problem is, if the absolute value of x is equal to 1, that means that my ratio test is inconclusive. So I actually don't know the results when the absolute value of x is equal to 1 in this case. And that would be when x is -1 and +1. We just don't know. So with my interval of convergence, I already have a good idea, but I still have to check the endpoints manually because ratio test is going to fail there. So we say, okay, that's fine. Test them manually. Let's start with x equals -1. What I want to do to test these manually is to go back to the original series. And that was the sum from n equals 1 to infinity, I believe. That was x to the n over 9n minus 1. And I physically want to replace x with -1. So this is the sum from n equals 1 to infinity of -1 to the n divided by 9n minus 1. See, I'm replacing x with -1, so I get -1 to the n on top. And this is what I want to look at. So now I have a regular looking series, right? Not quite a power series, and I want to test this. Notice it's an alternating series, so I'm going to use alternating series test, AST. So first, I want to sort of look past the alternating sign, which is this -1 to the n, and I want to focus on my b sub n. B sub n is this 1 over 9n minus 1. And I want to know, is this decreasing? So we could model this by some function of continuous variable x, 1 over 9x minus 1. Or I could write this as 9x minus 1 to the power of -1, all to the power of -1. And I can find the derivative. So f prime of x is going to give me -1 times 9x minus 1, all to the power of -2, and then times the inner derivative, which is 9. Or I could write this as -9 over 9x minus 1 squared. We'll say, well, the derivative is negative. So since f prime of x is negative, this means my function is decreasing. So then I have that first condition that b sub n plus 1 is less than or equal to b sub n. So check. And then I want to take a look at the limit as n goes to infinity of b sub n, which is 1 over 9n minus 1. And as n goes to infinity, this is going to go to 0. So this is convergent by alternating series test. So actually, -1 works. I checked the endpoint. I converge at that endpoint. But now I want to go through the same trouble, the same process, to take a look at x equals +1. And I'll do this in a different color just so it stands out a bit. We like purple. We like purple. So now I want to look at x equals +1. So this is going to be the sum from n equals 1 to infinity of, and it was x to the n over 9n minus 1, but now x is +1, so 1 to the n. So imagine going here and plugging in 1 for x, 1 to the n over 9n minus 1. And 1 to the power of n, it's always going to be 1, right? 1 to the first, 1 squared, 1 cubed, 1 to the fourth, 1 to the fifth. It's always generating a 1. So this is actually, it's not necessary to even write this as 1 to the n. We would just simply write this as 1 over 9n minus 1. And I want to do a test on this. I think this is going to be good for, one of those comparison tests. I'm going to try the direct comparison test and see if it works for what I'm trying to do. So I'll pick on 1 over 9n minus 1. And I'll compare it against 1 over 9n. And I have to put my inequality somewhere here. So here I'll look at the left-hand side. I'll say smaller denominator, bigger fraction. And remember, if we're not sure, we could always test a first value, right? When n is 1, this is going to give me 1 over 9 minus 1, or that's 1 over 8. This is going to give me 1 over 9, and 1/8 is greater than 1/9. So then, what we're looking at here, we can now start thinking about how it's going to look as series. So I could say, well, if I look at this one, I'll say, well, the sum from n equals 1 to infinity of 1 over 9n, or if you want to sort of see it a bit better, you could actually bring the 1/9 out. Say the sum from n equals 1 to infinity of 1/9 times 1 over n. This is divergent. And this is a divergent p-series. You could really sort of call it out as being a coefficient times the harmonic series. So divergent p-series with p equals 1. Harmonic series is relevant here. So this is divergent. And what I'm comparing it against, this sum from n equals 1 to infinity of 1 over 9n minus 1 is going to be greater than this sum term-wise. So I'd say, well, greater than divergent must also diverge. So this also is divergent by, and I like to call this the direct comparison test, to sort of distinguish against the limit comparison test. So here we have something is divergent. So what do I know now? Well, I know, switch back to yellow, x equals -1 is convergent. That was a convergent alternating series. X equals +1 was divergent. I was able to use the direct comparison test for that. So my true interval of convergence actually isn't what I wrote earlier, right? This is just what I had to work with the information that I had so far. So I'll actually go here and say, well, this isn't telling me the entire story. It gave me a good starting place, a good framework, but I can actually include -1. So I give that a square bracket. And then +1, I still want that rounded parentheses. I can't include that. But this is my true interval of convergence. Everything between -1 and 1, but also including the endpoint at -1, not including the endpoint at +1. Let's take a look at another example. So here we have the sum from n equals 0 to infinity of x to the n plus 1 over 4 times n factorial. And just to sort of, I'll clarify this when I write it out because I don't think this is ambiguous, but it's not 4n quantity factorial. It's 4 times n factorial. But what I'm looking at is my a sub n. So that's x to the n plus 1 over, we have 4 times, and then this is n factorial. And so then a sub n plus 1, that's going to be x to the power of n plus 1 plus 1, just replacing n with n plus 1. And then divided by 4 times, and this is going to be n plus 1 factorial. And I could clean this up. I could say, okay, this is x to the power of n plus 2 over this 4 times n plus 1 factorial. And now I'm ready for ratio tests. So I'll say limit as n goes to infinity, absolute value of, and I want a sub n plus 1 on top. So that's x to the n plus 2 divided by 4 times n plus 1 factorial, and then divided by a sub n. A sub n is x to the n plus 1 over 4 times n factorial. And again, I don't want to divide by a fraction. If we get comfortable with ratio tests, we might even start by multiplying by the reciprocal if we get good with what we're doing. So I have x to the n plus 2 over 4 times n plus 1 factorial, and then times, on top I'm going to have 4 times n factorial divided by x to the n plus 1. And I want to keep going with this. I want to break this up as much as I can, keep working with it. So I'll say limit as n goes to infinity, absolute value of, let me break this up, x to the n plus 2, I could say that's x to the n times x squared. And similarly, I'll sort of jump around, not literally, but jump around my work. X to the n plus 1, that's x times x to the n. Here I have 4 times n factorial. I'm going to rewrite that on the second fractions numerator. And then 4 times n plus 1 factorial in the first denominator, I'm going to write that as 4 times n plus 1 times n factorial, just breaking up the factorial like we've done earlier in previous videos. Now, a lot of stuff's going to cancel, so, get your Gatorade. Get ready for this. Get your Doritos. X to the n on top and bottom is going to cancel. 4 on top and bottom is going to cancel. N factorial on top and bottom is going to cancel. And I can reduce the x squared over x. So I am going to reduce that as well. So we'll say, well, this is going to give me the limit as n goes to infinity of the absolute value of x squared over x gives me x on top, divided by n plus 1. And let me just write this a little bit differently. So we'll say this is the limit as n goes to infinity, absolute value of, we have 1 over n plus 1, and then times x. Now as n goes to infinity, n plus 1 goes to infinity as well. 1 over n plus 1 goes to 0. So this gives me absolute value of 0 times x, which gives me absolute value of 0, which is just 0. So I get 0 out for my result. And remember what we were saying earlier, this usually gives us some condition to work with. This is what I'm getting for my limiting value, capital L. This is a special case, though. This is a special example, different from the one that we just saw, and different from the next one we're going to see as well, because this is actually a numerical value. Usually we get some variable left over, something in terms of x. But I can see in the line right before, well, x is gone because I had 0 times x. 0's got that, that power. Multiplying by 0 really kind of, changes things, right? Changes us. But so here we're saying, okay, this time I actually got a numerical value out. And remember what we say about ratio test. If L is less than 1, then we have the absolute convergence. And this is less than 1. 0 is less than 1, right? So what this means is our result, our power series, is absolutely convergent. And there's no sort of discussion that I'm having to have with the result that I got out of here. Ratio test is sure of this. It's saying, okay, you got 0. 0 is less than 1. You're absolutely convergent. There's no restrictions. There's no qualifiers. There's nothing to consider, which I think gets a little confusing now because, well, how am I going to build my radius and my interval of convergence? But here's where we just want to interpret what's happening. And it's actually going to be quite quick. Since we had nothing else to say other than, okay, the result was 0, 0 is less than 1, we have absolute convergence of our power series, that means the radius of convergence is capital R equals infinity. It's convergent everywhere. The radius of convergent is infinite. So we have this absolute convergence with no qualifiers. Similarly, the interval of convergence is, we'll do capital I, from negative infinity to positive infinity. And there's a bit of a bonus here. By bonus, I mean nothing else to do, because I can't check the endpoints. They're not finite numbers. I can't plug them in. This is the entire real number line. So we're actually done at this point. This one is actually a bit shorter because I can't physically check endpoints. I would want to, but I can't do that in this case because it's everything. It's convergent no matter what, which was one of those 3 possibilities. And this extra page here, we're not going to need it, so let me just write a note. You are the coolest for taking a look at power series with me. Thank you. Let's take a look at one more example, and we're going to move on. You know how we do this. I want to find the radius of convergence of the power series, sum from n equals 1 to infinity. We have negative 1 to the power of n, and then we have n to the 5th, x to the n, all over 7 to the n. So a lot of cool stuff going on here. What I'm staring at is a sub n, is this negative 1 to the n, times n to the 5th, x to the n, over 7 to the n. And a sub n plus 1, well, that's going to be replacing every mention of n with n plus 1. So negative 1 to the n plus 1. We're going to have n plus 1 in parentheses to the 5th. X to the n plus 1, all divided by 7 to the n plus 1. And let me go ahead and start working with ratio tests. So we'll say we want the limit as n goes to infinity, the absolute value of, and I'm going to do a sub n plus 1 divided by a sub n, since I see I'm going to be dividing by a fraction, let me sort of preemptively multiply by the reciprocal. So I have -1 to the n plus 1 times n plus 1 to the fifth times x to the n plus 1 all over 7 to the n plus 1. And I'm going to multiply by, and I'm going to flip this preemptively. So I'm going to have 7 to the n on top, divided by, I'm going to have n to the fifth, x to the n, and -1 to the n on bottom. Now the alternating sign, we can actually make quick work of it. If you'd like to, you could break it up and reduce, and then you could sort of cancel. I think that's perfectly reasonable. But keep in mind, a -1 to some power is either going to be +1 or -1. If it's +1, I don't need it. If it's -1, I got bad news. It's inside the absolute value, and that's no place for a -1 to be hanging around. So it's going to go anyways. But you could do similar ways of reducing like we've done previously and see it eliminate that way. I'm just going to go ahead and say it. It's inside the absolute value, so it's not going to want to stick around. But otherwise, so we'll say you're gone, absolute value is a bad place for you to hang out. Well, let's clean up the rest of this. So I have n plus 1 to the fifth. X to the n plus 1 is x times x to the n. 7 to the n plus 1 is 7 times 7 to the n. And I can leave this stuff the way it is. I can just rewrite it. And what else is going to cancel? Well, do this in a different color so it stands out a bit. Get some pink. X to the n on top and bottom is going to cancel. 7 to the n on top and bottom is going to cancel. And it looks like what we're left with is what we're left with currently. So we're left with the limit as n goes to infinity, absolute value of, and here I have a 1/7. I have n plus 1 to the fifth divided by n to the fifth, and I also have this x. Trying to make sure I didn't forget anything. N plus 1 to the fifth, I got it. X, I got it. 7 in the bottom, I got it as a 1/7. N to the fifth, I got it. We're all there. And since this n plus 1 and the n are both to the exponent of 5, I can actually group them together with that same exponent. So say limit as n goes to infinity of, we have 1/7. And then I'm going to have, in parentheses, n plus 1 all over n, and that's all to the power of 5, and then times x. And this, I can actually break up the fraction. So break up the fraction. Limit as n goes to infinity. Absolute value of, we have 1/7. This is going to be n over n, which is 1, plus 1 over n. That's all to the fifth times x. And we'll say, okay, well, let's talk about this. As n goes to infinity, 1 over n goes to 0. So it's going to give me absolute value of 1/7 times 1 plus 0 to the fifth, and then times x. So, okay, 1 plus 0 is 1, 1 to the fifth is 1, so that just gives me 1, and I have 1/7 times x. So this is going to give me absolute value of, we could write this as x over 7. Or if you'd like to, you could even say, well, 1/7, the 7 in the denominator is positive, so I could actually write this as absolute value of x, then divided by 7. And this is my limiting value, capital L. Remember, we're saying if L is less than 1, that's where we have that absolute convergence. And this doesn't give me a numerical value out. It gives me something still in terms of variable x. So I have to work with this a bit more. I have to sort of play around with it and get a result from it. So in order to get this to converge, and I'm interested in convergence here, I need this to be less than 1. And depending on what x is, it will be. For example, if x is 3, this will work. If x is 4, it's going to work. If x is 500, it's not going to work. So I gotta sort of work with this and say, well, okay, so this means if the absolute value of x divided by 7 is less than 1, I'm going to get absolute convergence. Let's see if we can solve this for x. So what we can do together, me and my cat crew here, is we can multiply both sides by 7. What do you think about this, Lily? What do you think about the power series? She likes them. She likes them. I like them too. The important part of, working with mathematics, working with power series, is always take the appropriate time out to, hang out with, if you got pet cats, if you got dogs, if you've got other kinds of pets. If you don't got pets, get some pets. Make sure that you're not neglecting them. Just the littlest babies. All right, ready to do this? Huh? Yeah, let's do it. We're going to multiply both sides by 7. So we're going to get an absolute value of x less than 7. And now this looks like a radius of convergence for us. That's right. So we're going to say the radius of convergence is capital R equals 7. So as long as x is between -7 and 7, this is going to work. And we get a sort of, working interval of convergence to start. I want to improve on it. We'll say interval of convergence, question mark, is capital I equals, right now we're going to say we know anything between -7 and +7 will work. But I'm not sure about the endpoints. And I don't know if this is true. I need to actually see if I can do any better. So we check those endpoints manually. Let's take a look at x equals -7. Now this means I want to go back to my series. That was the sum from n equals 1 to infinity of -1 to the n times, what do we have? N to the 5th, x to the n over 7 to the n. N to the 5th, we have x to the n. I'm going to just write that as blank parentheses now, over 7 to the n. Because what we're doing is we're physically replacing x with -7. So instead of x to the n here, I'm going to have -7 to the n. And there's a few things that are going to happen. But I could actually break this up. I could say the sum from n equals 1 to infinity of, I have -1 to the n, I have n to the 5th, -7 to the power of n, I could write that as -1 to the n times 7 to the n all over 7 to the n. And here's what we can say. 7 to the n over 7 to the n are going to cancel. And -1 to the n times -1 to the n is going to just be a +1. Because they're always going to be the same, right? It's -1 to the n twice over. You combine them and see it as an even exponent is a great way to see it. But I might even go so far as just to argue, if they're both +1, I don't need them as factors. If they're both -1s, they're going to multiply to give me a +1. But sure enough, if you want to write this as, -1 to the n and then squared, or if you want to add the exponents, there's so many ways to sort of justify this. But all this stuff is going to cancel except for n to the 5th. So this really just boils down to the sum from n equals 1 to infinity of n to the 5th. Now, we've been talking about series for a bit now in our videos. Do you think that this is convergent or divergent? It's definitely divergent. And we can use the test for divergence to show this. So we'll say, since the limit as n goes to infinity of n to the 5th is infinity, the series is divergent by test for divergence, TFD. If you think about this, this is going to grow very out of control. And if I'm supposed to be adding those terms together, there's no way that it's going to stop. The sum's going to keep growing and growing. I wish it was my bank account, but it's definitely not convergent. That's for sure. That is for sure. And then let's take a look at the other endpoint, x equals +7. So now I'm going back to my series. We're saying the sum from n equals 1 to infinity of -1 to the n times n to the 5th times x to the n, all divided by 7 to the n. But remember, for x to the n, I'm replacing x with +7 now. So we substitute that in. And this is going to simplify pretty quickly as well. 7 to the n on top and bottom is going to cancel. So I'm left with the sum from n equals 1 to infinity of negative 1 to the n times n to the fifth. And this is what I want to talk about. Now this is an alternating series test, so I could use, this is an alternating series, so I could use alternating series test, but it's going to fail miserably. These terms don't decrease in magnitude as n goes on, and the limit's not going to work either. So really, we even want to go back, think more about that test for divergence. We would say, well, since, I feel like I already said this to y'all, but since the limit as n goes to infinity of n to the fifth is infinite, this series is divergent by the test for divergence. We'd say it fails, so alternating series test fails. Got divergence here again. Right? These are going to grow crazily, the terms are, and they're going to be alternating their signs. If I got to keep adding them, it's just going to be chaos. Nothing convergent about it. So okay, so what did we learn? What did we learn? We checked the endpoints. We said x equals negative 7, x equals positive 7 are both divergent, which means that our interval of convergence was actually correct. I have to check. I didn't know. We have to check it. Don't just, skip the work and assume everything works out, because that doesn't always happen. But in this case, it is just between negative 7 and 7. So we got those rounded parentheses. The endpoints both fail. Now we know. Let's take a look at 11.9 now. Here we're going to start talking about geometric series again. We're going to talk about representations of functions as power series. And this is going to help us segue into talking about Taylor series and Maclaurin series. So here what we're doing is we're taking advantage of a geometric series. So remember, that would have been the sum from n equals 0 to infinity. This is the geometric series. Of a times r to the n, which is going to look like a plus ar plus ar squared plus ar cubed, plus so on and so forth. And when this converges, it converges to a over 1 minus r. But we're looking at the special case of this where a is equal to 1. So if a is equal to 1, and we're also considering r equal to x, if I make those substitutions, if a is 1 and r is x, I get 1 plus 1 times x plus 1 times x squared plus 1 times x cubed, which is exactly what we're looking at here. And that when this converges, remember this converges when the absolute value of r is less than 1. It's convergent. Then I get a over 1 minus r, or in this case 1 over 1 minus x with these substitutions. And this is what we're saying here. And similarly here I'd say, well, a is 1, so I don't need it. And then r to the n is x to the n. So this is all that we're saying, is that we're looking at a geometric series, but now we're treating it as a power series, working with power series and geometric series sort of together. We say, and this is convergent when the absolute value of r, which in this case is x, when the absolute value of x is less than 1. So this is a very nice result that we get that we're going to work with. We have some nice theorems for power series. Now, we're not going to really spend too much time talking about these, but the idea is that we have these power series that are differentiable. I can take derivatives of them term-wise, or I can differentiate the closed form as well. I could also integrate my power series, and I could integrate them term-wise, or I could integrate the closed form of it. Don't forget that arbitrary constant c, big C. And here just talking about what we've already discussed, talking about the geometric series. Now in this case, we're going to be able to actually build a radius of convergence and an interval of convergence right away. But you're going to notice something about what we're going to do in this section is we're not checking endpoints. There's a reason why. We checked endpoints in the last section because we were using ratio test. Ratio test is inconclusive when L is equal to 1. So I had to check my endpoints. we're not going to need to check endpoints because they're going to fail. They're going to fail because we're using a geometric type series. A geometric series is only convergent if the absolute value of r is less than 1. Not if it's equal to 1, not if it's equal to -1. It's not going to work, right? So in that case, we'll say the endpoints are going to fail whenever I'm doing this geometric series workaround. If you want to check, if you forget, there's no harm in that. You're just going to always see that they always diverge. So there's really no point to checking the endpoints for this kind of material. But what's going to happen is we're going to be given a rational function, and we're going to want to try to modify this into the form 1 over 1 minus x. Though more realistically, we're going to try to get this in the form 1 over 1 minus stuff. And this is going to be convergent when the absolute value of stuff is less than 1. And we're going to be able to build a power series from this. The sum from n equals 0 to infinity of stuff to the power of n. And this is what we're going to be working with. So this is what my goal is. And I have this rational function. Let's see what I can do with this. Let me just rewrite it. X over 4 plus x squared. I want to make sure I have a 1 in the numerator. I don't have a 1 in the numerator. I have an x in the numerator. So all we do is we bring the x out. We say x times 1 over 4 plus x squared. Okay, so far so good. Also, I got 1 on top. I also want this 1 on bottom. I need this 1 on bottom. I don't have a 1, I have a 4. So we got to bring the 4 out. Bring the 4 out. So now I have x over 4 times, I have 1 over, this is 1 plus, and since I brought the 4 out of the 4, I have a 1, but there's no 4 here with the x squared, so to compensate, I want x squared divided by 4. And you can either think about how this is going to work when I distribute the 4 back in. 4 times 1 is 4. Here the 4 over 4 cancels. Or if that's difficult to see, we could just, theoretically go to x squared and say, well, let's multiply cleverly by 4 over 4. Now I can factor that 4 out, and I'm left with x squared over 4. Another way to look at it. I'm actually pretty close to where I want to be. But I want this to be 1 over 1 minus stuff. And I'm sort of ignoring this x over 4 temporarily. I have 1 over 1 plus stuff. How do I get that subtraction there if it's an addition, if it's not subtraction already? Well, the answer may surprise you. I just introduce the double minus sign. We say 1 over 1 minus negative x squared over 4. And now I have that subtraction there. I need 2 minus signs since it was addition, but this does what I needed to do. And now I got it all. I really want to focus, though, on what my stuff is. We have 1 over 1 minus stuff. And this is my stuff here. And now I can start to say all these wonderful things about the result. We can say this is convergent when the absolute value of stuff is less than 1. And here that's the absolute value of negative x squared over 4 is less than 1. And I can work with this a bit more. So negative inside an absolute value, it's no good. And I can bring the 1/4 out. So we'll say 1/4 absolute value of x squared less than 1. I can multiply both sides by 4. So here we'll say absolute value of x squared less than 4. And I can take square roots on each side and say absolute value of x then is less than 2, which gives me a radius of convergence. My radius of convergence is capital R equals 2. It also gives me an interval of convergence without hesitation. My interval of convergence is capital I. It's from the interval from -2 to 2, and I need those rounded parentheses. Remember, this is not ratio test. I don't check endpoints because it's going to fail at the endpoints because I'm modeling this by a geometric series. And there's one more thing that I can do here is I can actually write the power series. Now to write the power series, I don't want to forget about this x over 4 that I had in front. So my power series is going to be x over 4 times the sum from n equals 0 to infinity of stuff to the power of n. And my stuff was this negative x squared over 4. Now, you could leave it like this. This is the power series. I don't think it's the nicest looking, so I would probably clean this up a bit. I would say the sum from n equals 0 to infinity of, here I could say negative 1 to the power of n, so I can see that alternating sign separately. Here I have, let me write the x over 4 in front. I'll deal with this in a bit. Here I have x to the 2n divided by 4 to the n. So I got negative 1 to the n, x to the 2n, 4 to the n in the bottom. Now I can bring this x over 4 in safely, and I can get a really nice final representation of my power series. All the cats today. It's my cat Gabriella. She's helping out. She wants to do power series with us. She's saying bring that x over 4 in. So I'll say sum from n equals 0 to infinity. We have negative 1 to the n. X times x to the 2n is x to the 2n plus 1, all divided by 4 times 4 to the n is going to give me 4 to the n plus 1. We're just hanging out here, having a good time. And this, I think, is the nicest representation of the power series. Was there anything wrong with this? No, not really. But you know I'm crazy, so I'm going to do what I think is right. Let's see another example. Remember, the goal is 1 over 1 minus stuff. So I'll even just jot a little reminder up here. 1 over 1 minus stuff is what I want. Right away, I can see an issue. I have x over, I can see a few issues, right? X over 8x squared plus 1. This x on top, I want it to be a 1. Just bring the x out. Bring it out like a coefficient. And then I have 1 over 8x squared plus 1. Now here's where we get into a bit of sort of, choppy territory. I want it to be 1 over and then 1 minus stuff. I have the 1 on top, but in the bottom, this isn't a 1. It's an 8x squared. However, the term right next to it is already a 1. So here we're going to do a very sneaky trick. I'm just going to go into the denominator and reverse the order of the subtraction. So instead of 8x squared plus 1, I'm going to say 1 plus 8x squared. It's the same, right? The order that we add doesn't matter. 2 plus 3 is the same as 3 plus 2. No issue in doing this. And it actually saves us a lot of headache because now I have 1 over 1 plus stuff. I want this to be minus, so I just have to introduce that double minus sign. And then I should be good to go. So x times, we have 1 over 1 minus negative 8x squared. And now I want to see, okay, so I got my 1 over 1 minus stuff. I want to make sure I know what the stuff is. Here the stuff is negative 8x squared. Now we can start talking about this. We can say all those lovely things we like to say. This is convergent when the absolute value of stuff is less than 1. And I can work with this a bit better to get a radius of convergence. First of all, the minus sign's gotta go. It's in the absolute value. The 8 then can come out as positive 8. Absolute value of x squared less than 1. Now I can divide both sides by 8 and say absolute value of x squared less than 1 over 8. And then I can take square roots of each side. So we can say absolute value of x less than square root of 1 over 8, which I could then use the quotient property of the square root, say square root of 1 over square root of 8, which is 1 over square root of 8. Might not be a bad idea to get, rationalizing with this. So we would say, well, let's go ahead and multiply then by square root of 8 over square root of 8. This is going to give me square root of 8 divided by 8, but I can bring a perfect square out. Square root of 8, we could say 8 is 4 times 2 over 8, and I'm still going with it. Can't stop, won't stop. Hashtag can't stop, won't stop. Absolute value of x is less than. Here I can use the product property of the radical. Say square root of 4 times square root of 2 all over 8. Square root of 4 is 2, so 2 radical 2 all over 8. I can reduce 2 over 8 by 2, so I get radical 2 over 4. Looks good to me. So now we can say, okay, so absolute value of x must be less than radical 2 over 4. And this gives me my radius of convergence. My radius of convergence, capital R, is radical 2 over 4. And it gives me my interval of convergence as well. Remember, I'm not using ratio test, so I don't have to check endpoints. I know the endpoints are going to fail miserably, that I'll diverge at the endpoints. So just a rounded parentheses. My interval is from negative radical 2 over 4 to positive radical 2 over 4. And now one last thing for me to do is to write the power series. Now I had a coefficient though. I don't want to forget about the coefficient when I do this. My coefficient was x, so it's going to be x times the sum from n equals 0 to infinity of stuff to the power of n. And what was the stuff? The stuff was negative 8x squared. And you could leave your power series like this, but I think it's better to clean it up. So what would I do? I would say x times the sum from n equals 0 to infinity. I would say negative 1 to the power of n. I would then say 8 to the n. And then x squared to the n is x to the 2n. And now I'm going to multiply that x in, bring it in, because I don't want to have it as a coefficient. So I would say this is the sum from n equals 0 to infinity of negative 1 to the n times 8 to the n times x to the power of 2n plus 1. And this I think is the best. The reason why I didn't leave it as negative 8 all to the power of n is because now I can see the alternating sign separate from these powers of 8 that I'm going to be getting. I just think that's a little bit nicer personally. Does it really make a difference? No. I think you'll be fine. I think you'll be fine. I think you'll be fine. But let's take a look at one more example. Let's find a power series representation for the function 6 plus x all divided by 1 minus x. Now right away, what I'm going to do is I'm actually going to break this up into two fractions. Say 6 over 1 minus x plus x over 1 minus x. And I'm almost actually where I need to be with this. I can bring the 6 out and say 6 times 1 over 1 minus x, plus here I can bring the x out and say x times 1 over 1 minus x. And for each of these, I'm very lucky because for each of these, my 1 over 1 minus stuff, my stuff is just x. So let me actually, I've been circling this in the neon pink, so I'll do that. 1 over 1 minus stuff, 1 over 1 minus stuff. And since it's identical for both of these, I can actually talk about them together in just one line of work. So this is convergent when the absolute value of stuff, the absolute value of x in that case, is less than 1. And this is already solved, so I can go right to my radius and my interval. My radius of convergence is capital R equals 1. My interval of convergence, and remember, no need to check endpoints because I'm not using ratio test. That's capital I, that's from negative 1 to positive 1 with the rounded parentheses. Now I want to write my power series. And when I go to write my power series, this is where we're going to see a bit of an issue. Don't forget about the coefficients. So here I have 6 times the sum from n equals 0 to infinity of stuff to the n, which is x to the n, plus here I have x times the sum from n equals 0 to infinity of stuff to the n, which is also x to the n. But when I go to bring this x in, and I can bring the 6 in as well. Let me do that for each of these. We'll say the sum from n equals 0 to infinity of 6 times x to the n plus the sum from n equals 0 to infinity of x times x to the n is x to the n plus 1. I want to try to write this as one power series, but the different exponents on x are what's sort of preventing me from doing this. So there's a couple of things I could do here. What I could do is I could start working with shifting indices and trying to see if I can get, the same exponents here. Another consideration, and I think a really good idea, would be to actually physically remove the n equals 0 term here. So what I'm going to say is well, let me go here and let me take out the n equals 0 term, which would be 6 times x to the 0, which is just 6. And now I'm going to keep the starting index at 0, but I'm going to shift this n to an n plus 1 because I don't have to start right immediately at the first term anymore. And I'm sort of talking about it colloquially right now, but I can actually show you why this is working and how it works the way that it does. So I'll say, let me bring out when n equals 0, I get 6 times x to the 0, which is 6. I'm going to bring that out. And I'm going to add it in manually. I'm going to say 6 plus, and then I'm going to leave the sum starting at 0, but now it's going to be 6x to the n plus 1. And this one, I'm just going to leave it alone. I'm going to say, okay, this one can just stay as the sum from n equals 0 to infinity of x to the n plus 1. Let me bring this full circle and then, double back. So, because now what I can do, since both of these are x to the n plus 1, I can add them. So I have this lone 6 that I picked out, but then plus I have the sum from n equals 0 to infinity of 6 times x to the n plus 1 plus 1 times x to the n plus 1 gives me 7 times x to the n plus 1. And this would be a great final answer for that power series. It's nice because if I want to test it, if I wanted to sort of present it, I could actually sort of look at this infinite part of it. I do have this extra loose addend, but this isn't really affecting convergence or divergence. I just have to remember whatever I get from this, I'd have to add a 6 to it. But this is very nice because now I have one infinite series instead of two infinite series. But if you're looking at this thinking, okay, well, you lost me, if that's fair, let's actually dissect it a bit. There's no shame in writing these puppies out longhand. So when n is 0, I get 6 times x to the 0, which is 6, plus when n is 1, I get 6 times x to the first, which is 6x, plus when n is 2, I get 6x squared. When n is 3, I get 6x cubed, and so on and so forth. But what about for the other one? Well, let's write that one out. When n equals 0, I get x to the 0 plus 1, or that's x to the first. When n is 1, I get x to the 1 plus 1, or that's x squared. When n is 2, I get x to the 2 plus 1, that's x cubed, and so on and so forth. And I'm trying to add these two things together. So if I add these together, let's do green. Gotta get some green action. If I add these together, I want to add the like terms. So I have this 6 as the only constant, so it's sort of just loitering. But then 6x plus x is going to give me 7x. 6x squared plus x squared is going to give me 7x squared. 6x cubed plus x cubed is going to give me 7x cubed, and so on and so forth. So now we can sort of see this in a bit of a different way. That it's really, I have this 6 that's sort of, by itself, because everything else has got a coefficient of a 7. And then I can write the rest of it as the sum starting at n equals 0 to infinity. And then I could do 7 and then x to the n plus 1, since I want to start it as x to the first. And this, I think, is a great way to write this. It looks really nice. There are tons of other ways you could go about writing this. Let me know in the comments below what you're thinking about writing this down as. But you could definitely get away with some very interesting stuff. You could actually manipulate this constant term here to get something that maybe even looks even nicer. So I wouldn't say not to do that, definitely. I would say go for it. Some consideration there. But I'm already thinking about it. I want you to think about it. Let me know if you can find an even nicer way to write this. But right now, I'm feeling good, feeling great about this. I have this extra blank sheet of paper here. I just want to write you a note. Thank you for hanging out with me, hanging out with the cats and I. Had a lot of fun doing this. Love talking about these power series. Let me know how you're doing. But otherwise, make sure that no matter what, no matter where you are, keep learning, keep dreaming, and always follow your heart. I'm going to be back doing more math with you soon. But until then, I want you to take care of yourself. And hey, I'll see you soon, so don't go anywhere.